Hello everyone, and welcome to our webinar entitled The Circular Carbon Economy and the 4 Rs: Reduce, Reuse, Recycle and Remove. My name is Jim Herbertson and I'm the Technical Director for Climate and Energy here at IPECA. Before we start, I would like to cover a few housekeeping items. The webinar is being streamed through your computer, so there is no dial-in number. Everything you can see, including the slides, is resizable and movable, so feel free to move things around and get the most out of your screen. At the bottom of your screen, you will see some features that are available. You can use the Q&A box to ask questions as we go. The slides are available in the resource list if you would like to download them. Also, there is a help feature, but most issues can be sorted by refreshing the page using the F5 key. This is particularly useful if you think your slides are falling behind. A recording will be available later this week and can be accessed using the same link you are using now. And now I'd like to say a few words about IPECA for those of you who are not familiar with the organization. IPECA was formed in 1974 following the launch of UNEP, the United Nations Environment Programme. We are the only global association for both the upstream and downstream oil and gas industry. Our membership operates worldwide, and we reach about 500 oil and gas companies when we include the reach of our association members. Our work encompasses 4 broad themes: climate, environment, social responsibility, and oil spill preparedness and response. We are the industry's principal channel of communication with the UN and work closely with a number of UN bodies. We present and hold side events at the UNFCCC COPs, the Conference of the Parties, and at the UN Convention on Biological Diversity, at the UN Environment Assembly, and the UN Business Council on Human Rights. Access to affordable, reliable energy is essential for the growth of strong economies, long-term improvements in health, quality of life, and the eradication of poverty. Supporting the transition to a lower emissions future, while ensuring there is substantial energy to meet the needs of the world's growing population, is key to delivering sustainable development. IPECA members recognize they have a crucial role to play in supporting the energy transition and contributing to sustainable development. One of our recent activities has been to map the oil and gas sector to all 17 of the UN Sustainable Development Goals via our SDG Atlas, which we put together in conjunction with the UN Development Programme and the World Bank IFC. And we are currently working with the World Business Council on Sustainable Development on an oil and gas sector roadmap for the SDGs. We are not an advocacy organisation, we are member-led, and we concentrate on technical and fact-based information. We use our convening power to bring together professionals from the member companies to work together to develop and share good practice. This enables the industry to improve its environmental and social performance. We also look to enhance and share knowledge on topics of interest, hence our webinar today. During this webinar, we will hear about the circular carbon economy and the 4 Rs: reduce, reuse, recycle and remove. We are joined by Tijani Nias of Saudi Aramco, who will be our presenter today. I'll let Tijani introduce himself in a moment. Our moderator for the Q&A session afterwards will be Arthur Lee, who is the Chevron Fellow and Senior Technical Advisor on Climate Change. And now over to you, Tijani.
Thank you, Jim. So just in few words, my name is Tijani Nias. I work with Saudi Aramco since 2008, mostly in the area of sustainability. I held many leadership positions in R&D strategy development for the company. So before Saudi Aramco, I was with IFP, Institut Français du Pétrole in France, where I spent around 15 years working mostly in process and chemical engineering. I left IFP as the head of the chemical engineering department in 2008. So Just to begin with, let me first welcome you to the webinar, and good afternoon and or good morning, depending on your location, and hope you are keeping safe and healthy in a post-COVID-19 recovery world, as we all hope. So I would like first to thank IPICA for giving me the opportunity to present to its member today. Thank you, Jim, for facilitating this, and thanks also to Arthur for his role as a moderator. I hope you will find today's talk beneficial for you and your organizations. So in today's talk, I want to cover 3 main points. First, introduce the concept of circular carbon economy, or CCE in short, and its 4R principles. Second, explain why circular carbon economy is important for both climate and energy challenges. And third, provide examples from my company, Saudi Aramco, of technology solutions that demonstrate the value of circular carbon economy for a sustainable energy system. So let's start. I think important to remind everyone at the beginning that as the backbone of the modern society, hydrocarbons have enabled global prosperity, lifted billions of people out of poverty, facilitated people and good mobility, improved quality of human life on Earth, and empowered people. This was achieved through the extraction of oil and gas natural resources, their transformation and use, which generates CO2 emissions that are released to the atmosphere. Okay. So while this make dispose linear economy model was very economically efficient because of cheap hydrocarbon energy resources, it was based on 2 fundamentally wrong assumptions. So the first wrong assumption is it assumes we have limitless hydrocarbon energy resources. Although this assumption is absolutely wrong, it was still fine with a limited number of modern energy consumers. But now we know that increased number of energy consumers through the growing world population will put significant pressure on the global energy system and accelerate resource depletion. Second wrong assumption is the limitless capacity of the Earth system for absorbing waste CO2 emissions resulting from the use of the hydrocarbon energy resources. Since the Industrial Revolution, the Earth's atmosphere has become one of the largest depository of our waste, with billions of metric tons of greenhouse gases accumulated in the atmosphere, causing risk for irreversible climate change if we exceed the threshold of 450 ppm CO2 concentration, which is equivalent to an increase of around 2 degrees Celsius above the pre-industrial levels, according to the Intergovernmental Panel on Climate Change, IPCC. These 2 issues are creating important sustainability challenges on the global energy system and threatening the quality of our life on Earth. For our global energy system to be sustainable, we need to meet 2 important imperatives. Imperative number 1 is we have to address the fair need of energy access for billions of people, mostly in the developing world, by providing them with reliable and affordable energy. In the International Energy Agency IEA 2019 stated policy scenario, global primary energy demand will increase by 25% by 2040. The IEA estimates that today, more than 2.6 billion people still don't have access to clean energy, cooking fuels, and around 840 million people still don't have access to electricity, with the vast majority from Africa. Imperative number 2 is to deliver the needed energy in a way that preserves the environment and address the risk of climate change. This graph shows the effort we need to take collectively to reduce emissions from current policy trajectory to a level that is consistent with the Paris Agreement, while allowing energy access in a scenario called SDS, Sustainable Development Scenario. I heard recently someone saying that it might be true that people will be dying in the future because of climate change. But for sure, people are dying today because of energy poverty. And that's the dilemma we face all. So we should address this dual challenge of clean energy access and climate change in a more holistic way than our current practices. Solving this dual challenge will require a paradigm shift in the way we address both energy and climate issues. And there are several elements that support this need for a new paradigm. I will just name a few. First, emissions have been fluctuating since 2015, despite an international agreement set to limit the increase in the global average temperature to well below 2 degrees Celsius above pre-industrial levels, the so-called Paris Agreement. Second, the global energy system is complex with interdependencies and energy products traded across the globe. There is a big difference between the real energy system and the theoretical ones as we design them in our offices and laboratories. In the refining industry, for instance, we have to balance geographical shortage on gasoline and diesel. Third, the scale of climate challenge is huge. The World Bank estimates at $90 trillion the need for climate-resilient infrastructure investment by 2030. For example, the needed carbon capture and storage capacity alone to deliver on the Paris Agreement ambitions is at the scale of today's oil and gas industry in terms of volume. That is very massive. Very significant investment in renewable energy and energy efficiency in the range of several trillions of US dollars are also needed. Many key economic sectors are constrained and hard to decarbonize. This includes power, industry, and transport. Indeed, dispatchable power requires storage, which is not available today and will be challenging to implement at grid scale. In the industry, cement, steel, and chemicals are all constrained, while their product will be essential to support economic growth. In few vital cases, the CO2 is not linked to the combustion of a fossil fuel, but from the process itself. A good example is cement industry, where more than 50% of the CO2 emissions are from the decomposition of calcium carbonate to calcium oxide. Heavy-duty transport, aviation, shipping are all struggling because of lack of technological solutions, although offsetting options are being considered in these sectors. However, there is a hope with hydrogen in industry and transport, but economics and policy have to be improved for mass adoption. Hydrocarbons continue and will continue to play a significant role in the global energy mix for decades to come. Substitution of fossil fuel will require time, money, and technologies that are often not available or economical today, limiting deployment opportunities. Examples include energy storage, CCS, and hydrogen. Most of current climate policies focus on reducing fossil fuel demand only, undermining the potential of carbon recycling and removals. These are the gaps that circular carbon economy approach is trying to address. At Saudi Aramco, we believe the circular carbon economy can be the solution for the dual challenge of providing clean and affordable energy to the growing world population while addressing GHG emissions. A circular carbon economy adopts the principle of a circular economy, emulating the balance of nature in its production, use, and reuse of energy and materials. I will explain now how a circular carbon economy is different to the well-known circular economy. As we all know, a circular economy is a system designed to minimize resource consumptions and waste disposal, mostly implemented in the waste management industry in the 70s. The focus is on resources and material flows, and the system is based on three principles: reduce, reuse, and recycle, the three R's. A circular carbon economy is an all-inclusive approach that values all options and encourages all efforts to mitigate carbon accumulation in the atmosphere. It focuses on energy and carbon flows. A circular carbon economy adds a fourth R, remove in the 3 R's of the circular economy, making it 4 R's: reduce, reuse, recycle, and remove. Given the global economy reliance on hydrocarbons with decades of investment in energy infrastructure, we believe the circular carbon economy offers a holistic and pragmatic approach for managing greenhouse gas emissions in a closed loop involving the 4 R's. In the next slide, I will define each of the R's and provide examples of technology solutions under each of the R's. Reduce under a circular carbon economy framework involve all options that reduce the amount of CO2 entering the atmosphere. Examples of mitigation options under reduce include energy efficiency, non-biomass renewables, nuclear power, CO2 capture from stationary sources such as industrial facilities or mobile sources such as ships, heavy-duty trucks, and fuel shifting from coal to gas in the power sector, for instance, and hydrogen. Reuse under the circular carbon economy framework involves using CO2 without changing its molecular form. CO2 is not chemically reacted. Examples include most of today's use of CO2, such as dry ice, blanketing, fire extinguisher, etc. So this represents around a few hundred of million tons of CO2 per year. Supercritical CO2 applications, such as in the power sector, where CO2 can be used as working fluid instead of steam, as in conventional steam cycles. The US-based company Net Power is piloting this technology in Texas. CO2 enhanced oil recovery, where CO2 is injected in maturing oil fields to improve the extraction of the remaining oil. In this process, part of the injected CO2 remains permanently trapped underground. Recycle under the circular carbon economy involves turning CO2 into new products. The CO2 is chemically reacted in this step. Examples under recycle include synthetic fuels, fertilizer and urea, methanol and chemicals production, polymers and concrete. In most of these cases, cheap renewables energy is needed for the chemical reaction to provide a real climate benefit based on a comprehensive life cycle assessment. Remove under a circular carbon economy involves taking CO2 out of the atmosphere. Examples include direct air carbon capture with storage, DACs, bioenergy with CCS, BECS, and natural climate solutions, NCS, such as reforestation, soil, and oceans. All combined together, this is how a circular carbon economy framework may look like with the 4 R's: reducing, reusing, recycling, and removing greenhouse gas emissions in a closed loop. We believe this framework offers a holistic and pragmatic approach that integrates all energy sources and value all emissions mitigation efforts, allow the optimal use of existing energy infrastructure and value decade-long investment in the energy system, address emissions in hard-to-abate sectors by building a carbon reuse and recycling economy, and enable negative emission technologies that are crucial for meeting net zero emission target. This slide shows an example of energy and emission flows based on the Energy and Resource Institute TERI scenario. It integrates all energy sources and emissions mitigation options to achieve balance between emission sources and sinks. In this example, carbon utilization estimates are from the IEA, and the direct air carbon capture is calculated for carbon balance. The circular carbon economy is a G20 priority for this year in both climate and energy working groups, with an objective to build consensus around needed policies, technology innovation, and collaborations. I have the privilege to be part of those meetings, and there is certainly a growing interest from G20 members on the circular carbon economy approach. Japan already established a circular carbon recycling initiative under their Ministry of Economy, Trade and Industry (METI). They focus on the production of CO2-free hydrogen and zero carbon electricity supply as enablers for chemicals, fuels, and mineral production. The U.S. Department of Energy held a summit in 2018 on realizing the circular carbon economy. Discussion focused on how to integrate nature-based solutions, renewables, and carbon capture in a view to balance emissions between source and sinks. In 2018, the Oil and Gas Climate Initiative introduced the Net Zero Pathway under the title Towards Circular Carbon, focused on improving energy efficiency, providing clean and affordable energy, capturing, storing, and using CO2, and balancing remaining emissions through the NCS. Many other countries and institutions are adopting the circular carbon economy concept or some element of it, as this is seen as a pragmatic ways to achieve carbon neutrality. In the next slide, I will describe initiatives and technological solutions that address GHG emission across the 4 Rs using Saudi Aramco initiative as example, but I'm sure you have similar examples in your own organizations. Under reduce in upstream and midstream operations, I will start with the challenge Saudi Aramco faced in the 70s that has similarities with today's CO2 challenge. As you may know, prior to the 70s, the prevailing practice worldwide in the oil industry was systematic flaring of associated gases, as there was no economical solution to utilize them. Without any environmental pressure, Saudi Aramco embarked into a major initiative to capture and monetize its associated gases through the establishment of a master gas system across Saudi Arabia. This master gas system reduced flaring from 4.2 billion scf standard cubic feet a day to less than 200 million scf a day, representing around 95% of the associated gases captured. This initiative captured and monetized associated gases across the Kingdom of Saudi Arabia, contributing to economic diversification, job creation, and improving quality of life through improved energy access and water access also. We call it an emission to value. So this master gas system is one of the largest industry projects in the world, with more than 4,000 kilometers of cross-country pipeline, 50 gas oil separation plants, 7 large gas processing plants, 7 power plants, 2 desalination plants, and availed about 13 billion scf of associated gases as feedstock for chemicals. The initiative demonstrated how we could make value from emissions and contributed to avoiding about 98 million tons of CO2 per year, or more than 3.9 gigaton of cumulative CO2, which is more than 70% of today's world road transport CO2 emissions from light duty and heavy duty sector. Another initiative under review is the establishment of our corporate energy management program in 2000, which focused on minimizing our flaring to near zero through a flare recovery program, building cogeneration plant, improving our plant efficiency, and the use of best appliances in our offices and communities. Using cogeneration, we achieved 100% self-sufficiency in electricity generation for our operation. Our installed power capacity is more than 6.5 gigawatt, and we export a significant share of it to the Saudi national grid. The total CO2 emission avoided from this program is another several hundred of million tons of CO2 since 2000. The impact of this initiative in reducing our emissions are significant, as Saudi Aramco achieved the lowest upstream crude carbon intensity of any major oil producer and roughly half of the global industry average, as highlighted in this graph from a publication by Stanford University in Science magazine. Saudi Aramco reported third-party verified carbon intensity is 10.1 kilogram of CO2 equivalent per barrel of oil produced. To put this in perspective, in a scenario where the global upstream crude oil carbon intensity matches that of Saudi Aramco, the resulting greenhouse gases emission savings is estimated at about 1 gigaton of CO2 equivalent per year. So this is equivalent to the development of 650 CCS facilities of about 1.5 million tons of CO2 storage capacity worldwide. Another recent paper published in Nature Climate Change on carbon intensity of global crude oil refining and mitigation potential shows that shifting to low carbon intensity crude can help the oil industry save between 56 and 79 gigaton of CO2 by 2100. Having troubles. Jim, I'm having troubles moving to the next slide.
Johnny, we're on reduce sustainable transport technologies.
Oh, okay. So from my screen, I don't see it. So then, okay. So maybe you can take the control. Okay, hang on. Let me see what's. Okay. So anyway, so and under reduce in the light duty, which slide do you have, Jim, in front of you?
Slide reduce sustainable transport technologies. If you want me to move the slides, just say so.
Okay, all right. So under reduce in the light duty transport sector, while we recognize that electrification is progressing, we believe the biggest scope for reducing light duty transport emissions remains improving the efficiency of internal combustion engines. At Saudi Aramco, we are developing novel technologies such as gasoline compression ignition engines, or GCI in short. These engines burn gasoline in the traditional diesel compression ignition platform, resulting in significant efficiency improvement and reduced CO2 emissions. We already demonstrated 30% increase in fuel mileage compared to naturally aspirated direct injection baseline. This is our first generation technology which we are working on with automakers for vehicle demonstration. We are also developing a second generation using more advanced combustion systems that would achieve 40 miles per gallon increase in fuel mileage. Next slide, please. Jim, next slide, please.
Yes, it is showing there may be a delay on the system, as we've told people. So this is reduce and talking about sustainable transport technologies. You want to move to the next one?
All right, okay. Another example of efficiency improvement to reduce in the transport is the opposed piston technology with a demonstrated 33% increase in fuel mileage compared to gasoline US light duty trucks. Next slide, please. Now we are on the sustainable transport heavy duty mobile carbon capture, Jim.
Correct.
So as we discussed earlier, the heavy duty transport sector is constrained and abatement solutions are limited. Electrification would not make sense here in the short term, but carbon capture could be a viable solution in these long haul trucks. We are developing onboard carbon capture systems for heavy-duty trucks using the available waste heat to separate CO2 from other gases, compress it, and store it on board. So the CO2 can be discharged at the gas station during refueling, gathered from several trucks and transported to a storage location or utilized on-site to produce low-carbon products or fuels using cheap renewable energy. Our first demonstration prototype achieved 42% CO2 capture from a heavy-duty truck, and we are also working on developing a second generation targeting 50% CO2 capture. Next slide, please. On the hydrogen space, We believe hydrogen can play an important role in reducing emissions in many industries, including transport through fuel cells. Hydrogen can be produced through excess renewable electricity using electrolyzer or through methane stream reforming associated with carbon capture, the so-called blue hydrogen. We recently inaugurated the first hydrogen fueling station in Saudi Arabia in partnership with Air Product. The pilot station will fuel an initial fleet of 6 Toyota Mirai fuel cell vehicles to be tested in real Saudi environment conditions with high purity compressed hydrogen. Next slide, please. On CO2 sequestration, under reuse where CO2 is utilized without changing its molecular form, we have been piloting carbon capture and reuse for enhanced oil recovery since 2015 when we began injection. I have to stress that CO2 EOR is not needed for production at scale for decades to come, given the vast oil resource we have at Saudi Aramco and our low production cost. But using our in-depth expertise in reservoir management, we decided to build this pilot and contribute to the improvement of knowledge in the field of CO2 sequestration in our field. The project captured 800,000 tons of CO2 from an NGL plant, transported through 85-kilometer pipeline where it is injected in Osmania field. This is one of the most sophisticated CO2 EOR projects in the world, as it has more than 1,000 sensors to monitor the CO2 plume and provide extensive data on CO2 storage. The amount of CO2 stored is above industry standards through the use of a comprehensive monitoring and surveillance program. Next slide, please. Under recycle, where CO2 is utilized as feedstock and chemically reacted, in 2016 we acquired the polyester business from a US-based startup company. This technology, named Aramco Performance Materials, converts CO2 into cleaner, high-value end product with significant performance, cost, and carbon footprint improvement using a proprietary catalyst. The polyester product contains up to 40% CO2 and can be used in many industries to produce foams, coatings, elastomers that we use in our daily life. Another exciting project is our yesterday announcement for CO2 to fuel in collaboration with Repsol. This project will combine green hydrogen produced from renewables with the CO2 captured from Repsol Bilbao refinery to produce more than 3.6 million liters of fuels per year for vehicles and aircraft. Next slide, please. Now I'm under recycle. Something that I'm very excited about is under recycle is the use of CO2 in concrete and cement and concrete. This technology is extremely important given the fast-growing need for infrastructure and building. Today, water consumption for concrete curing represents more than 3 trillion liters per year. We are developing solutions that utilize CO2 for concrete curing instead of water. Saudi Aramco has its own CO2 to concrete technology, but through the Oil and Gas Climate Initiative, we invested in Solidia technology that produces concrete containing up to 70% CO2 and reduces 80% of the water consumption for curing. According to Solidia, their technology has a potential to eliminate a minimum of 1.5 gigaton of CO2 each year. Next slide, please. So under remove, we are developing breakthrough materials for direct air carbon capture. These functionalized metal organic framework materials have very high absorption capacity that can be combined with cheap energy to improve the economics of direct air carbon capture, which is essential for offsetting some of the hard-to-abate sectors such as aviation. Next slide, please. Still under remove, another exciting initiative is mangrove and tree plantation, nature-based solutions. Mangroves play an important role in carbon sequestration, up to 100 times faster and more permanently than terrestrial forest. We have planted more than 2 million of mangroves across the kingdom, both removing CO2 but also protecting sensitive areas of biodiversity. We also planted over 300,000 trees and planning on increasing this effort. Next slide, please. With that, I conclude my talk. Thanks for listening and wish you safety. Hope you enjoyed it. So back to you, Jim.
Thank you, Tijani. A truly wide-ranging and very thought-provoking presentation that raises all sorts of interesting questions for our Q&A session. Before I hand over to Arthur, just a quick reminder that you can still use the Q&A facility within the webinar platform to ask questions. It's located at the bottom of your screen. It looks like we already have some questions in, so over to you, Arthur.
Thank you very much, Jim. You can hear me, I suppose?
Yes.
Loud and clear.
Okay, thank you. I have a serious question, but I'd like to start with some of the more broader overview type questions, and then get down into details if I could. So one of the questions that a commenter has here is about the terminology itself, about remove. The 4 R's. I mean, we have the first 3 R's that are well known, and then the 4th R is remove. One of the commenters wants to express a difference of opinion with you, and said that isn't remove something similar to disposal? Are we actually thinking of the 4th R as really disposal? So over to you, Tijani.
Well, we recognize that under each of the R's, there might be different definitions based on the options that are available to everyone. Under remove, in our definition, the CO2 has to be sucked from atmosphere in order to balance between hard-to-abate sectors and the things. So the fundamental idea behind the circular carbon economy is to make sure that the 4 R's work together, addressing both the potential for reducing emissions, reusing them, recycling them, and then removing them from atmosphere using nature-based solutions or direct air carbon capture.
Thank you very much, Tijani, for addressing that question. I also have a question about a fairly broad question. Hopefully, you can address it. That the technologies and even the techniques that you are talking about, perhaps more into the recycle and the remove part of it, is this question from a commenter about the maturity. If you can address about the maturity and the proven nature of some of these technologies or techniques. How proven are they? How mature are they?
Well, there are different levels of technology readiness level under recycling CO2. I would say CO2 to concrete is something that is getting to a higher TRL level. There are considerations for large-scale pilot demonstrations. CO2 to fuels still require significant investment in R&D, where innovative or breakthrough catalysts are needed to convert CO2 into fuels or polymers. Because as you know, CO2 is at the bottom of the CO2 doesn't have energy. So for CO2 to be converted, you need to overcome the thermodynamic barriers, and this is where innovation in the area of catalysts is very important. So we, under the Mission Innovation Carbon Capture Initiative Challenge, we have identified a number of areas for improving the thermodynamic and chemistry of CO2 conversion to fuels and chemicals and even to concrete. Those are at different level of maturities, but some of them, like I said, can be considered today. Another good example is the use of CO2 in its supercritical form for power generation. The pilot plant that is being operated by Net Power is a big one, 10 megawatts, using gas turbines, using turbines. I'm sorry, with CO2.
Thank you, Tijani. Let me follow up on that a little bit with a question from another commenter. It's about the markets for some of these things like concrete. So if we are in the happy circumstance of these technologies working very well to reduce CO2 and putting into concrete, but what size of these markets are we talking about that we can materially reduce CO2 and putting into cement and concrete? What do you think of the market effects of that?
Well, actually, I thank you very much, Arthur, for this question. Very interesting, because the size of CO2 utilization market is quite significant. The Global CO2 Initiative has did a comprehensive assessment of CO2 utilization in the concrete industry, chemical industry, fuel industry, etc. So they have came up with three major utilization prospect that has impact at a gigaton per year of CO2. That include concrete and cement, chemicals and fuels. In both cases, the numbers, if you take, for instance, the CO2 to concrete, the size of that market is in the range of 7 gigaton of CO2 per year. The Solidia assessment is 1.5 gigaton of CO2 per year. So those numbers, if you put them in the context of the IPCC or the IEA scenarios, they are at the scale of what CCS as industry should be delivering around 2030, 2040. So the size of CO2 utilization is significant. So, and I think that this point is very important, because it shows that, if really we develop these technologies and make them commercially viable, then building a recycling, a CO2 reuse and the recycling industry would make a lot of sense.
Great. Thank you. Thank you very much, Tijani. There's a related question from one of our commenters. It's about the range of the carbon removal technologies and methods that you talked about, ranging from natural climate solutions to what we just talked about now, about the recycle of it. Can you comment on, expand a little bit more on the feasibility of the techniques to remove carbon?
Well,
economic feasibility. Yeah, economic feasibility.
Yeah. Sure. The one that I'm most excited is direct air carbon capture. Today, there are several pilot demonstration plants in North America and Europe that are capturing CO2 directly from air at a cost between above 500, let's say, $500 to $600 per ton of CO2 captured using those techniques. But listening to the expert working on those technologies, there is a tremendous opportunity for cost reduction to bring the cost of capture down to 150 to 200 in the next 5 years. So that's very exciting. That's very interesting technology that can be utilized. Bioenergy with carbon capture is another also technology that has interesting prospect. Cost is much less than the carbon capture from air, and the natural-based solutions include a variety of solutions that most of them can be made economical today if the right policies are put in place.
Thank you for
We're
that.
getting there.
Yeah, great. Yes, thank you for addressing that. I have a question a little bit more specific now. What would you say to a commenter who really wants to know what are the, if we do adopt these approaches of the 4 Rs, what would be a good set of metrics to measure a company's performance in adopting the 4 Rs? What would be a good set of metrics?
I think a very good metrics for the circular carbon economy is the amount of CO2 that is being reused, recycled, and then removed through these 4 Rs into the economy. So today we have an existing infrastructure in place. So there are multiple ways to get to any climate target. If you look at the IPCC scenarios, I think there are more than 400 different pathways that can take you to a 2-degree scenario or to a 1.5-degree scenario. Both can achieve the target, but the cost is absolutely different. And according to some studies, the cost could be more than 140% higher based on the pathway that we adopt. So what is exciting in the circular carbon economy is to recognize that how we can make the best use of existing infrastructure. And a good metric would be when we design a material, we don't design it like we don't design it as like end of life. We design it to be utilized for another process. CO2, for instance, can be captured from power plant, from industrial facilities, can be combined with hydrogen, for instance, to produce a variety of chemicals or fuels. So that percentage could be a very good reflection of how much carbon we are recycling into the economy. So we need to have those policies that feed each other's and then enable each other's. Right now, most of the policies are on the reduced part, but if we find a way for policies under reduced to enable the other 3 Rs, reuse, recycle, and then remove, then we'll have a carbon flowing across the economy, and then make the best, achieve the climate targets earlier than let's say building a completely new energy system from scratch.
Thank you for that, Tijani. I have a quick follow-up. A commenter wanted to know now more specifically, what is the goal for Saudi Aramco itself as a company in terms of total greenhouse gas emission reduction? Can you state such a goal?
Well, we are part of. Unfortunately, I cannot talk specifically about Saudi Aramco's goals in terms of carbon emissions, because this is being discussed internally and being finalized. But we are part of the OGCI. We are playing a leading role under OGCI, and under OGCI, we aspire to work with all stakeholders in order to bring the emissions down to a level that is consistent with the ambitions of the Paris Agreement. So Saudi Aramco is part of that family, and we are availing our expertise across the energy system to make sure that we get to that target.
Okay, thank you for addressing that. Johnny, I want to broaden, sorry, I know I narrowed it down quite quickly, and apologies for that. Let me broaden up the question a little bit. There is a commenter here who wants to know a little bit more about the life cycle aspects of even removing CO2. When you are using CO2 to make new fuels, for example, in your relationship announced relationship with Repsol, you're going to make new fuels from CO2. So can you address more about the life cycle aspects of using CO2 and then make new fuels and the life cycle emissions of that as well?
Yeah. Well, CO2 utilization in the form of reuse or recycling has to go through a comprehensive life cycle assessment in order to assess the climate benefit. And this is maybe one of the gaps that we need to address collectively in the industry to agree on the assumptions and the methodologies to assess this life cycle across the value chain of CO2. So there are different carbon footprint, but for sure, if you're using a CO2 that is produced from a low carbon intensity crude, then the impact in terms of carbon benefit using life cycle will be much higher than if you're using a higher carbon intensity. And this is what I was alluding in the presentation when I talked about the Saudi Aramco carbon intensity. When it comes to more specifically to the project that we have with Repsol, I don't have specific numbers in terms of impact through a life cycle to communicate because this is just from yesterday. The exciting thing is that we will be using CO2 capture from a refinery combined with renewables to produce fuels. So which type of, depending on where you take the CO2 in the refinery, the life cycle could be completely different. But I would advise the one who asked the question to follow up with us in the future once we'll have better clarity on how what's the impact of those fuels will be in terms of carbon footprint.
Thank you, Tijani. I'd like to there's another commenter who wants you to think more about other industries and perhaps speculate how this would apply. So this commenter wants to know whether the 4 Rs can be applied and how would it be applied, you think, to the aviation sector? For example, even the reuse principle for the aviation sector.
So the obvious answer to that question is through offsetting using natural climate solutions. This is one solution. Another great opportunity under this circular carbon economy for aviation would be direct air carbon capture, where you capture directly the CO2 from atmosphere, compress it, and then store it underground, and that could offset emissions from aviation. I think in the International Aviation Organization, they are looking at CORSIA, under CORSIA, at different mechanisms to produce low carbon fuel, including offsetting as I described.
Great, thank you for that, addressing the aviation industry. There's a little bit more specific question under reduce now. Under reduce, for example, in our refineries and petrochemical facilities, what are some of the examples that Aramco is thinking of in terms of using renewable energy to power units in a refinery or petrochemical facility?
Well, we're finalizing a set of options to reduce further down our emissions in Aramco. But the examples that I provided through our master gas system and energy efficiency program is putting us really at the forefront of the industry when it comes to upstream carbon intensity. So Saudi Aramco is enjoying today the lowest crude carbon intensity of any major oil and gas company, and we believe that if we can help other oil-producing companies get to the level we are in Saudi Aramco, that would save gigaton of CO2 annually. There is a very important also prospect to integrate renewable energy in our operations, and this is being discussed these days. And we hope with that we will take further down our carbon intensity to levels that will demonstrate that we can make fossil fuels very clean in addressing the climate change.
Great. Thank you for that, Johnny. I have a question here about again, it's actually a question about another sector. How do you think this could be applied also to automobile manufacturers in terms of the 4 Rs? Would that how would it apply to them? If especially when they're going for electrification, as some of them are, and some of them are going to hydrogen. So with that range of options, how does the 4R apply to the automobile manufacturers?
Yes, so thank you for that. I think in the transportation sector for automobiles, energy efficiency, improving the efficiency of today's engines has a significant potential to save emissions. In addition to other technologies that are being developed. So the example of producing synthetic fuels or e-fuels through the collaboration that we're building up with Repsol, I think is a great initiative for the auto industry. Hydrogen also is another interesting, important fuel for the auto industry. Hydrogen can be produced today through methane steam reforming with carbon capture at a cost that is much lower than the cost of producing hydrogen from renewables with electrolyzers. So we need to materialize those low-hanging fruits that are just next door by deploying technologies that produce hydrogen from fossil fuel with carbon capture, or make use of CO2 with the hydrogen from renewables to produce e-fuels. So this is for the transportation. But in the area of heavy-duty trucks or ships, where technological solutions are not always economical or available, carbon capture could be also a viable solution. And the business models that I described, where the CO2 is captured from a truck or a ship and is stored on board until the next destination, where the CO2 can be collected from multiple trucks and then being transported for a storage location, or being utilized in conjunction with renewables to produce e-fuels, will help the heavy-duty sector and the shipping reduce their emissions. So just in a nutshell, though, I think there is a great prospect for the transport industry to adopt this circular carbon economy framework, where reduce and reuse or recycle can be utilized together to reduce the emissions.
Great, thank you for that very comprehensive answers. Sure, we all appreciate that. I have a question here, perhaps a little bit broader, back to a little bit broader scope. Now, of course, we are all familiar with government regulations and policies to reduce, tell industry to reduce emissions. So how do you think government policies here will play, either collaboratively or maybe in other jurisdictions more adversarially, about the 4 Rs beyond reduce, recycle, remove? How do you think government policies will evolve with these 4 principles?
I think this is really at the heart of today's discussion. Let's first recognize that, current government policies are mostly focused on reducing energy demand from fossil fuels. And in my opinion, this is really undermining the potential of reusing, recycling, or even removing CO2 from the atmosphere. So there is an important need to innovate in terms of policy design in a way that whatever tax or credit is generated from reducing emissions is being utilized to enable the reuse or recycling or removing CO2 from the atmosphere. So the good thing in the circular carbon economy is that it's based on very strong or comprehensive life cycle assessment, and then recognize that things doesn't have the same impact on the climate. Storing 1 ton of CO2 in geological formations doesn't have the same climate impact in let's say storing the same amount of CO2 in a tree, for instance, or from recycling that CO2 into chemicals. So this is where the life cycle come into play. So government policies has to be designed in a holistic way, where we look at the entire CO2 value chain, from the reduce, reuse, recycle, and then remove, and then look at the climate benefit in order to make sure that that holistic approach is delivering climate benefit.
Thank you very much, Tijani. And with that, as a closing question, the last question, I will hand it back over to Jim Herbertson.
Thank you, Arthur.
Thank you. Thank you, Arthur. Okay, a huge thanks to Tijani, our presenter today, and for answering so many and such a broad array of questions. And thanks to Arthur for moderating the Q&A session, and thanks to all of you who are on the line. As mentioned earlier, a recording of this webinar will be available in the next couple of days and can be accessed on the same link as the live webinar. Thanks again, have a great rest of the week and stay safe.
Thank you.